Yeah, I also saw, yeah, Lily's in the audience. Lily's another co-PI, yeah, in the tripod. So she's in the professor in the stats department. So just a quick introduction.
Sure.
Hi.
Hello.
Hi, good afternoon. Look forward to your talk.
Thank you.
21 people now, so maybe we can start introducing Ness while people are coming in.
Still joining, yep.
Okay, so, let me start. So hello everyone, good afternoon. Today it's a great honor to have Professor Ness Shroff from Ohio State to hold this distinguished lecture in the CS department at ISU. So many of you may know that Professor Shroff is a very well-known researcher in our community. So his CV his bio is pretty long, so I will only select a few highlights. Professor Shroff received his PhD degree from Columbia in 1994, and then he joined Purdue afterwards. And then in 2007, he joined Ohio State. He holds a joint appointment in ECE and CSE. So Professor Shroff's interest spans a lot of areas in communication, networking, storage, cloud, recommender systems, social networks, cyber-physical systems, and lately a lot of interesting problems in machine learning. So I think today his focus is more on load balancing, which is also a very, very interesting topics, and we will have a lot of impact in different areas. So he's currently the editor-in-chief of Arbitrary and ACN Transaction on Networking, which is the most prestigious journal in our area. And he also holds a few other editorialship positions. So I won't go through all of them. He has also received a lot of best papers, and the list is too long to enumerate. And he's a fellow of IEEE, and he was a National Science Foundation Career Awardee. And I want to highlight that Professor Shroff is on the list of highly cited researchers from Thomson Reuters, ISI, and he's one of those, the world's most influential scientific minds, according to Thomson Reuters. He also received this IEEE Infocom Achievement Award for seminal contributions to scheduling and resource allocations in wireless networks in 2014. So all these are remarkable achievements. So without further ado, let's welcome Professor Shroff to start his seminar. So Ness, the floor is yours.
Thank you, Kevin, for this very kind introduction. So I am very sorry that I cannot be at ISU in person, because it would have been fantastic to visit the university and meet all of you. But hopefully we can start with this talk, and perhaps some collaborations and other opportunities will emerge along the way. All right, so as Kevin mentioned, today what I'm going to do is I'm going to talk about how to reduce delay in large-scale cloud computing types of systems through a technique called load balancing. And here are my principal collaborators of much of the work that I'm going to present. Also for the last part of the work, I should say that we also have an additional collaborator who is Adam Weirman from Caltech. But most of the work is done with these two. My student, Xingyu Zhao, who's the lead contributor, and one of my colleagues who's now gone back to industry, Dr. Jian Tan. So here is the basic outline of the talk, and I won't go through every detail, but I'll sort of begin with an introduction and motivation of why delay is important and why load balancing and what it is about. Then we'll talk about the system model and outline some of the key contributions of our work. Then I'm hoping that I'll have some time to kind of give you some high-level proof ideas and insights, and then we will look at some extensions, and finally I'll end with a summary and some open questions. All right, so let's begin with the introduction. So, as all of you know, I mean, if you've been alive in academia at this time, big data, machine learning has become sort of the flavor of the day, the flavor of the month, the decade, and so on. And it's to some extent for good reason. If you look at the volume of data that was generated from the dawn of civilization to about 2003, according to this website, it was 5 exabytes of data. And since 2003 to 2015, we've basically generated this much data every other day. Okay? And so over the last few years, since 2015 until now, you've seen a tremendous growth in cloud services that allow you to process, analyze, and support this data, which in turn means that the explosion has just continued at an even greater pace. So, and if you look at cloud services, they are becoming more and more ubiquitous. They are forming the core of many web-based services. It's not just IT industry that uses them. We use them in media, finance, education, electronic commerce, government, etc. But a big concern in many of these applications is to have low delay. So it's a very, very critically important consideration. And I'm going to give you a few examples where delay plays a significant role. So the first big example that I can think of is electronic commerce. So if you just look at 2018, the online US sales, and this is not global, it's just in the US, were roughly $500 billion. Okay. And as you can imagine, in COVID days, this would be much, much more in 2020. So what Amazon found was that every 100 millisecond of latency, additional delay, costs roughly 1% in sales. And so this is one of the reasons why many retail sites have worked very, very hard to try to reduce their latency, typically doing it through sort of software sort of updates, etc. So I'll give you an example. Walmart reduced its time to interact, which is the time when links become alive, from roughly 7 seconds to 3 seconds in a period of 6 months in 2014. So if you look at the Walmart website in 2014, on average, after 7 seconds, you'd still see a blank screen. And then at 7.2 seconds, you'd see the whole thing render. And so what they did was via software upgrades, compressing fonts, images, and so on, and showing things in a more sort of gradient way, they were able to sort of reduce this delay considerably. So after now 2.7 seconds, things started to become interactive. And this is true throughout the industry. So Google actually did a very interesting study where it took a subset of its users and provided them 30 results on its first page rather than the typical 10 results that we got. And that gave users far more accurate information to choose from, but the delay grew by a factor of 2. And Google found that when this delay grew by a factor of 2, the traffic on their websites, actually on their search engines, dropped substantially. So this tells you that users want low latency even more than they want additional and accurate results. And Google has been obsessed with reducing the web latency, and in fact, it even rewards its Google ranking algorithms. It rewards fast websites in its Google ranking algorithms. Another example is that of online gaming, which is has moved far and away from child's play. It's a huge business, growing fast. It's basically an industry that generated $100 billion in 2017, and it's primed to do much more than that in 2020. And there, what people showed was that, well, at least according to this website, if the delay grew by a factor of 2, the user playing time, reduced by a factor of 4. Okay, which meant that inducing, delays would be something that parents of children would be interested in to stop them from gaming, but generally that would hurt the industry in a substantial. All right, the final example that I'll give, and this is a very surprising example, comes from the high-frequency trading market. So according to a consulting company called the Tab Group, if a broker is 5 milliseconds behind the fastest broker on the market, that broker roughly will lose 1% of the high-frequency trading transaction flow. And a 1 millisecond advantage in trading can be worth $100 million a year to a major brokerage firm. And if you are 100 milliseconds behind, you're pretty much out of the high frequency trading market. So again, delay is very, very important. So what all these applications are telling you is that time is critically important. And in fact, how we reduce delay in large scale cloud computing systems is a very, very important objective to consider. And so the one particular approach, and we've taken several approaches in my own group to sort of consider reducing delay, but the one approach that I'll talk about today is called load balancing. And so let me begin by describing first a typical data center architecture in which load balancing plays a critical role. So if you look at, say, a data center architecture like Facebook, you will see that tasks arrive at a particular load balancer, which basically sends them to one of a series of load balancers, and from there you basically send a task to a series of servers. And in practice, the overall system may have many, many such parallel architectures. So each one of these you can think of as a cluster, and there are multiple clusters in a real system. And in all of these, it turns out that the building block is this load balancing element. Okay? So this load balancing element essentially takes a task and decides which of the servers to transmit to, and it's key to reducing the delay, improving throughput, increasing the reliability and robustness. So let's first focus on a single load balancer, this fundamental element, and let's develop results on that, and then I'll talk about extending it to sort of multiple load balancers, or what are known as multiple dispatches. So if you focus on a single load balancer, you can see that these tasks are arriving to a dispatcher, and the dispatcher needs to make a decision on to which of these servers to route them to. And you can think of each of these servers has a queue of tasks, and the tasks remain in their queue until the service is finished. So our system is a discrete time or time-slotted system where the aggregate arrival rate of tasks is given by this lambda sigma, and the service rate of each server is given by mu sub k. Both the arrivals and the service are general. I'll get into more detail about that. So we don't have any specific distributional requirements. And the goal of load balancing, as I mentioned before, is to choose the right server for each task in order to achieve high throughput, which is a large number of tasks per second being computed, as well as low latency. So what do we mean by latency? What constitutes latency or delay in this case? So it turns out that in these systems, you actually have two elements that constitute latency. One of them is called the dispatching time. So when a task arrives, It's the amount of time since a task has arrived until the task is sent to a server. So until it joins a server. So that part is called the dispatching time. And then there's another delay, which is called the response time, which is the time it takes for a task since it's joined a server to leave a server. And my question to all of you is, intuitively, what do you think, which load balancing policy would be a good policy to have in such a system? Anyone? So if you have a system like this, you have all these, tasks waiting in queue, where should you send it? What do you think is intuitively a good model? A good outcome? Join the shortest queue, right? If you just think about supermarket lines, intuitively, the line you would choose would be the shortest one, right? And indeed, this has been known for a while that this type of a mechanism does extremely well. In fact, 40 years ago, Foschini proved that joint shortest queue policy was delay optimal in heavy traffic and also in other domains. But this is only true from the point of view of the response. There is a potentially large dispatching time. That is, figuring out which of the queues is the shortest is a non-trivial expenditure of time. And this policy is almost never implemented because it's often impractical to implement. Because the message overhead turns out to be twice the number of servers. So about 25 years ago, okay, is there a question? Sorry, I'm hearing some background noise. Is there a question? Is there an echo? Okay.
Yes, sounds like some echo.
Yeah, maybe if people can
Oh,
mute.
Gianfranco, yeah, Gianfranco, it seems your mic is unmuted. Is that the problem? I'm not sure. Okay, yeah.
Yeah.
Okay.
Right. So, sorry to interrupt, but so about 25 years ago, Kellyan laws proposed a threshold type of policy to precisely try to sort of overcome this complexity issue. And we are going to call this policy join below threshold R, which basically means that a dispatcher chooses a server to join whose queue length is below R. Otherwise, the policy randomly joins any server. Now, it turns out that this policy can actually be initiated by the server itself, and so it has very low dispatching time. And the message overhead is also low. It turns out that, and this is not in the paper, but we can actually show that this is true, so it's a good policy. It's at most 1 per arrival. And in that paper, they claim that join below threshold policy is heavy traffic delay optimal if the threshold R is appropriately chosen. So in particular, if R is greater than log of the expected number of tasks in the system, then it works well. It turns out that in later papers, for example, T and Ward show that this policy, this result in Kelly's paper is not actually a proven result, it's only a conjecture. And there have been lots of efforts to try to prove the conjecture over the years. So the key question is, firstly, does the Kellyan law conjecture hold? Is it even true? And more importantly, does it hold for practical cloud computing systems where the load balancing system doesn't only have 2 servers, but it may have an arbitrary number of servers. It has not Poisson arrival and exponential holding times like it does in Kelly's paper, but you can have a general arrival process of tasks. In our case, we can handle all arrivals as long as they're light-tailed, and a general service time distribution, which means that the number of tasks per time slot at each server follows any general light-tailed distribution that you can think And it turns out that the answer to this question of whether the Kellian law conjecture holds is almost yes. And we'll show in what conditions is it yes and what conditions it's not. So the key contributions of this work are to establish necessary and sufficient conditions on the threshold for showing heavy traffic delay optimality in load balancing systems. So from a theoretical point of view, it resolves this long-standing open conjecture and provides, as you will see, some new insights into how heavy traffic delay optimality can be obtained through some new techniques for the analysis of these load balancing policies, where we sort of will develop a new type of what I will explain later as state space collapse. From a practical point of view, it allows the design of very simple load balancing schemes with very low dispatching time and low message overhead. So for example, Netflix had this question in its tech blog where it says that when possible, instead of configuring static thresholds, so they do believe that having a threshold-based policy is practically good, use adaptive mechanisms that can change based on the current traffic performance. However, they don't know how to choose this threshold, and this is an answer that we will provide. So before I do that, let me give you a little bit of background on heavy traffic delay optimality and also some different classes of load balancing systems. All right, so our goal really is to develop load balancing mechanisms that minimize the total delay in the system. In general, this is an extremely hard problem because even characterizing the exact delay is hard. This is true for almost any problem in communication systems. And so what we end up doing is we look at asymptotic regimes. And there are several asymptotic regimes in which people look at. One is the large system regime, where you essentially fix the load on the network and let the system grow. So in this case, for example, the number of servers would go to infinity. The many server heavy traffic regime, where you basically let the number of servers go to infinity as well as the load going to one. And then the regime that I will talk about in this particular talk, which is the heavy traffic regime, where you fix the number of servers and you look at the saturated case, which is sort of the most congested case, where the utilization is essentially hitting the boundary of the capacity range. So what do we mean by heavy traffic delay optimality? This slide kind of will give you a nice explanation of that. So let's say, for example, we have this system where you have the dispatcher with a particular arrival process of tasks that needs to decide which of these servers to choose. It turns out that the total delay in this system can be lower bounded by a resource pool system in which this server here has a service rate equal to the sum of the service rates of all of these servers. And you can show that this has a lower bound on the delay of this total system. And what heavy traffic delay optimality says is that your load balancing algorithm is heavy traffic delay optimal if in the heavy traffic, which is when epsilon goes to 0, where epsilon corresponds to the difference between the total service rate and the arrival rate, okay, the expected delay in this super server system is no better than the expected delay that you achieve with your load balancing system in this particular original system. So the idea is that heavy traffic delay optimality implies that your load balancing scheme can actually achieve the lower bound of the delay of this super server resource pool system in heavy traffic. All right, and our overall goal here is, can we develop simple load balancing schemes that are indeed delay optimal in heavy traffic? So now let me give you a little bit of a tutorial on what are the various classes of load balancing schemes that people use in the literature. So broadly speaking, load balancing schemes can be placed in two broad classes. And I'm using the terminology from the literature. So push corresponds to those schemes where the servers are responding to a polling request that is pushed to them from the dispatcher. So it's like the dispatcher sends out a signal, asks the servers for some information, and then the servers respond. And then pull corresponds to the servers themselves telling the dispatcher that they are ready for the task. So they're ready to pull the task. So the classic example of a push-based algorithm is join shortest queue, in which when a particular task comes to a dispatcher, the dispatcher polls all of these servers and then so pushes this request to the servers, and then the servers respond with their queue length. And we've already talked about the pros and cons of this scheme. And then, of course, the dispatcher sends the task to the server that has the shortest queue. Another algorithm, which is sort of a special case or a subset of the, actually it's a more relaxed version of the join shortest queue, is called the power of D. So instead of polling all of the servers, you end up polling only 2 or 3 servers in the system. So when the task comes in, now you basically, in this case, D is equal to 2. You send out a polling message saying, hey, give me your queue lengths, and once the servers tell you what their queue lengths are, the task is sent to the server with the shortest queue. And this algorithm also, in the homogeneous case, when all of the servers have the same computing power, does quite well. I mean, so for example, you can see that you can get double exponential decay in the delay tail when the number of servers is large, and in the homogeneous case, it's asymptotically delay optimal in heavy traffic. And while the message overhead is reduced by using something like power of 2 or power of 3, the problem is that there is still this non-trivial amount of dispatching. So the pull algorithms is sort of the other side of it. They try to sort of overcome this con by allowing the servers themselves to tell them when they are ready. So in this particular model, you can see that the dispatcher keeps in memory which particular queue is idle, 1 for idle and 0 for busy. And then a server will say, hey, I've just transmitted my packet, now I'm idle. So then the dispatcher will take that particular memory and then change it to 1. So, and then the dispatcher, when a task comes, when an arrival occurs, it routes it to the appropriate idle server. So it just picks any one of the servers that is idle. All right, and then of course, once it does that, it makes sure that it flips the bit of the server it's sent to and changes it to 0. You may ask, what happens if all the servers are idle or if all the servers are non-empty? In that case, it basically just transmits a task randomly to any of the servers. All right. So the good news here is that for medium loads, it actually provides better delay performance than a lot of the power of D policies empirically. But the bad news is twofold. It doesn't do well when you have non-homogeneous traffic, and it also, the performance, even in under homogeneous case, degrades substantially in the heavy traffic. So here's sort of the big picture. Push algorithms have good performance from the point of view of the response time in heavy traffic, but they could have large dispatching time, and they could potentially have large message overhead as well. The pull algorithms don't perform well in heavy traffic, such as JIQ, don't do well when you have heterogeneous servers, but have good performance in terms of low dispatching time and low message overhead. So the big question that one can ask is, can pull-based algorithms in fact achieve, small delays? And the answer is yes, if you allow for dynamic threshold. All right, so let's now look at a generalized version of the pull-based algorithms. But before that, I'm going to give you and that'll set up the necessary conditions. But before that, I'm going to give you a warm-up quiz. All right, so let's see who's been paying attention. So question A, is join idle queue delay optimal in heavy traffic? From what I said. Yes, no.
No.
Right, good. And the second question is, in the heavy traffic limit, is the delay under join idle queue the same as that under random routing? So let me ask let me sort of give you the intuition here. If the system is very heavily loaded, right, basically all of the queues will start to have packets or tasks in them. And in that case, join idle queue basically says, okay, I will just transmit to any one of them. So the question is, when you approach the heavy traffic limit, is the delay under join idle queue equal to that of the delay under random routing, or worse or better?
Yes.
Okay, so that's the yes would be the logical answer, but it turns out to be no. Right? In fact, we will show that in the heavy traffic, the delay of a optimal policy is strictly less than the delay of join idle queue, which is strictly less than a random routing policy. And so I'll explain how that will work. All right, so first, before I sort of show this result, let me first give you a description of the general pull-based policy, which is our join below threshold policy for any threshold R. So in this policy, the memory at the dispatcher stores the IDs of the servers whose queue lengths are less than R. And I'll explain the mechanism of doing that later. And if the memory is non-empty, the dispatcher randomly picks one of the IDs and sends the task to the corresponding server. Otherwise, the dispatcher randomly picks any server to join. Okay. So you can think of JIQ as a special case of join below threshold R with R equal to 1. Okay. And if the servers are heterogeneous, in this case, we can simply replace the pure random selection by a random selection that's linearly weighted by the service rate. So the probabilities are weighted by the service rate. All right, so let me kind of give you a little bit of an idea of the setup through kind of some geometric intuition. So for us to sort of maintain simplicity, let's look at a 2-queue system. Okay, so you can see Q2 on the y-axis, Q1 on the x-axis, and you can see that this is your threshold R. Okay, so R corresponds to the threshold. Basically below which you will transmit to any of them randomly. So you can see, for example, if the queue length vector is in this pink area, okay, it means that either all queues are below the threshold or all queues are above the threshold. And in that case, the policy simply reduces to random routing. However, in the white spaces, there is a drift towards choosing the shorter queue. So if you're in the white spaces, for example, if you're here, then you'll end up choosing Q1. So you push this in this direction. If there is so there's a preference for basically choosing shorter queues. So what are the necessary conditions for optimality of this policy? So let's kind of give the necessary conditions, and then I'll kind of give you a little bit of an intuition of how this all works, which will be related to the geometric condition. So consider a load balancing system under join below threshold policy. So now it says that for any constant threshold in heavy traffic, we have the following result, which says that the optimal delay is better than the delay that you will get in the join below threshold policy with this constant threshold, which it turns out to be better than the delay you will get in a random routing policy. Okay? So this is saying that if your threshold is constant, you're not very good, you won't get the optimal, but you'll at least do better than random routing. Then it's saying that if the threshold, on the other hand, is growing very, very fast, it sort of grows as 1 over epsilon to the 1 plus alpha. So basically, epsilon is the difference between the load and, I mean, the capacity and the load. Okay, and so it's kind of like how close you are to the heavy traffic regime. And 1 over epsilon is roughly the expected number of tasks in the system. So it says if your threshold is actually above this 1 over epsilon, then in fact you do much worse. Not only are you worse than delay optimal, but you're no better than random routing. So you don't need to do any of this fancy stuff. You might as well just do random routing. And you can see that R equals 1 is a special case of this JBTR policy. So JIQ, which happens for R equals 1, is also strictly between optimal and random routing. So we kind of showed why the original conjecture that we had was true, or we've stated it. But is there some intuition? Okay. And the answer is the King equation. So this is a particular equation which essentially provides you with the necessary and sufficient conditions for delay optimality in heavy traffic. And I won't go through this equation in detail or anything like that. The only thing I will say is that for each server n, it's always true that the queue length times this unused capacity must be equal to 0, because either you have something that needs to be served or you have no service. So it's basically when you multiply the product, one or the other of these terms is 0. The King equation requires the cross terms to be 0, which basically means that no server should be idling while other servers are serving lots of tasks. And that's roughly the idea of the King equation. Okay, so keep this intuition in mind, which is a necessary and sufficient condition for heavy traffic delay optimality. And now let's look at what happens when R is too large. So if your threshold is too large, then if you look at that geometric figure that I gave you, the threshold point will be here. Okay, so Q1 equals R and Q2 equals R is here. But the average number of tasks in the system is order 1 over epsilon. Okay, and in this particular case, if the threshold is growing as 1 over epsilon to the 1 plus alpha, this threshold is far above this average Q length. And most of the time, although you won't always be near the average Q length, you expect that you will be around this average Q length. So this means that almost all of the time, what you will be doing is you will be in this pink area. And therefore, your join below threshold policy simply degenerates to a random routing policy. Now let's look at the reverse figure. Okay. In this particular case, your threshold is very small. Okay. And your Q length now is in this domain, right? So you can see that in this case, join below threshold always has a chance to prefer the shorter queue because you're in the white spaces. So you can always choose. There's always some possibility that you will do better than random routing. However, this pink area, when this threshold is so much lower than the average queue length, okay, the pink area gets to be too close to the axis. So this means you cannot guarantee that all servers are busy when there are high loads. So it's basically what might happen is you might hit this point here, which means that Q1 is 0, or you might hit this point here, which means that Q2 is 0. So this is not optimal. It sort of violates the King equation. Of course, this is all high-level intuition, and the proof requires much more work and so on. So then the question becomes, how fast should the threshold grow? And this is where we come to the sufficient condition. So before we do that, let's look at the conjecture. Which of the following thresholds cannot guarantee optimality? So clearly, R equals 100 is a constant threshold, so that cannot guarantee optimality. Clearly, R equals 1 over epsilon to the power 1.01, that cannot guarantee optimality because it's going too fast, right? So it violates unnecessary conditions. But either of these two could be a potential candidate. And for, if we looked at the conjecture that we had 25 years ago by Kelly and Laws, they said that for a two-server system in continuous time, for Poisson arrivals and exponential holding times, this threshold must be greater than k times log of 1 over epsilon. And it turns out that that's almost true. So this theorem tells us that if you consider join below threshold with a threshold R, and you let R grow greater than some constant times log of 1 over epsilon, but smaller than 1 over epsilon, then join below threshold turns out to be heavy traffic delay optimal. And this is true for an arbitrary number of servers, true for general arrival and service time distributions. And there's an additional thing, which is that you can actually show optimality in steady state, which is in general kind of difficult with that. Okay. So this resolves a generalized version in discrete time of the Kelly and Laws conjecture. Now, what were some of the challenges? There are really two key approaches in the literature to showing heavy traffic optimality, and each has its own difficulties. The first one is the classic scheme, which is based on what is known as the diffusion approximation method, which essentially has this very complicated multi-dimensional Brownian motion, which is difficult to obtain, and generally interchange of limit arguments become quite hard, and it's very difficult to show this in steady state. Another approach has been to use a very recently developed approach about 7 years ago called the Lyapunov drift-based method. But standard techniques fail in our case because the state space collapse is not a line. And even though in later papers we ourselves extended it to a cone, it's neither a cone as well, the state space collapse, and I'll explain what that is. In fact, the state space collapse, actually in our case, turns out to be non-convex. So our approach uses this Lyapunov drift-based analysis to establish what is known as a new type of state space collapse and combines this with the Chernoff bound to get this result. So you might ask, you've talked about state space collapse multiple times, what is it? Informally, you can think of state space collapse to a subspace simply implying that the steady state Q length concentrates around that subspace. Okay, so for example, you can see if the subspace here is a line, the steady state Q length basically is in a small kind of range around this line. Same thing if the subspace, if the subspace is a cone, the steady state Q length is around the cone. And the idea is that the distance between the steady state Q length and that subspace has finite bounded moments, which is small compared to the average Q length. So it's kind of sufficiently away from the axis itself. So why is it important? Again, it's because of the King equation, right? So this is to make sure that you're around this line or around this cone where you're sufficiently far from either of these axes, at least 1 over epsilon, such that you guarantee that no server is idling while other servers have high loads. So in our case, what is the state space collapse? And as I mentioned before, it's neither a line nor a cone, and in fact, it hits the geometric figure that I drew initially. So if you look at only a 2Q system, this is what the state space collapse looks like. Okay, so remember that under join below threshold, the Q length vector lies in the pink area. The servers are chosen randomly, otherwise shorter Q is preferred. Okay, so hence, whenever the Q length vector is outside of the pink area, there exists a drift towards the pink area. And then we can show that all the moments, if you choose R appropriately, all of the moments of the distance of the Q-length vector to this pink area are bounded. So we kind of show the state space collapse. And I won't sort of go into the proof in great detail, but basically, if you write the expression of the King equation in the cross terms, each of these terms is symmetric, so you can pick one of them, and you can write them as a sum of two terms. And it turns out that the first term is less than or equal to 2R times epsilon, since the expected unused capacity is always less than epsilon. So this will go to 0 as long as R is growing slower than 1 over epsilon. And then your second term here, you can show that it's bounded by Cauchy-Schwarz and state space collapse to kind of by this expression. So here you can show that if you choose R sufficiently large, in this particular case, K times the log of 1 over epsilon, the second term will also go to 0. All right, so this sort of gives you some high-level intuition of this, but what is the practical implementation of joint below threshold? So one way to think about implementing it is that each server initially has an empty queue, and the corresponding bit at the dispatcher is set to 1. Okay, and then when a task arrives, okay, what the dispatcher will do is it will basically send it to one of the empty servers and then change it to 0. If all of the bits are 0 and 1, it randomly picks any of the servers to join. Otherwise, it picks one of the servers to join whose corresponding bit is 1. Okay. So in terms of the practical implementation, the way it works is each server reports its ID to the dispatcher or the load balancer at the end of each time slot, only if its queue length is below whatever threshold of R you've set, and the dispatcher does not contain its correct status. So how does it know? Let me give you an example. Let's say the threshold is 2, okay? And let's say that this server which had 2 packets in it, or 2 tasks in it, had one of them served. So now it went below the threshold of 2. So now this server tells the dispatcher, hey, change my bit to 1, okay? But this guy doesn't say anything, okay? Even though its threshold is below 0, because it already knows that the dispatcher knows this from a previous time. And this server N doesn't say anything because the number of tasks in its queue are greater than this threshold. So how do we choose the threshold? Well, one simple way is we can directly apply the sufficient condition, but this requires estimating the traffic load itself. If you can estimate it through measurements, great, you can apply the sufficient condition and you're done. If not, we have another way of doing this, which is a very simple implementation of a scheme. So what we can do is every T time slots, where T could be arbitrarily large but finite, we can randomly sample a subset of the queues, let's say D queues, and take the minimum of the queue length as the threshold. So this is a push-pull policy, which with the push part being very small. And this theorem provides something very interesting. It says that for any finite time T, and D even equal to 1, so it doesn't even have to be greater than 1, even equal to 1, this policy is throughput and delay optimal in heavy traffic. All right, so here are some numerical results where we essentially take this particular policy, JBTT, and implement it. And just for comparison, we basically don't consider the dispatching delay. So in that case, joint shortest queue is optimal. Remember, joint shortest queue has this big dispatching delay, so it's in practice, it's not optimal. But just to kind of get a comparison of the response times, we are just removing the dispatching delay from it. And you can see that even in this case, these simple joint below threshold type policies by sampling DQs turn out to work very, very similar to that of joint shortest queue, even in terms of response time. And of course, they do much better in terms of dispatching delay. And this is better than policies like power of 2 even with memory and without. This is just a zoomed in version where we can kind of show that even in the homogeneous case, when the traffic load is high, join idle queue kind of blows up. This basically shows that, when the load is fixed and the number of servers is fixed, even when we vary the number of time slots in which you do this update, okay, the policies achieve very good delay performance. So this basically tells you that our policies have low message overhead without incurring a lot of loss in terms of delay. Okay. All right, so I have a few more minutes. Next question is, what happens when you have multiple dispatches? Because in reality, there may be more than one load balancer in front of this layer 4 load balancer to determine which cluster, for example, this image request would join. Right? So you kind of see that you kind of have these multiple dispatches, and we need to figure out how to solve this problem. So from a practical point of view, what you want is you want these dispatchers to actually act independently of each other, because the communication between them is costly. It could be delayed, and it could slow down the performance. You also want to avoid herd behavior. So for example, if you have lots of dispatchers and all of them choose the same server to join, then it will cause local hotspots, because even though they might have very low queue lengths, you start joining those servers, all of a sudden their queue lengths blow up and you have a problem. In fact, as we will show through simulations, in practice, even from a response time point of view, join shortest queue, if you employ it in a multi-dispatcher case, because it creates this herd behavior, it actually performs quite poorly. Finally, you want to keep the message overhead as low as possible. All right, so what we will do is we will give a framework for choosing a policy that does well, as long as it satisfies the conditions of the framework. So this is the framework. This framework is called LED, so it's local estimation driven framework, where the memory at each dispatcher keeps local, possibly outdated estimates of the queue lengths for each server. And this LED policies have really two components. One is what is known as a dispatching strategy, which means when new arrivals come at the dispatcher, they are transmitted to a particular server based on what knowledge the dispatcher currently has of the estimate of the server. And then there is an updating strategy, which says that, okay, I'm going to update these estimates of the local queue with the real queue length. So the question is, how often do I need to make this estimate? How many times do I need to do it, et cetera, et cetera. And our goal is to develop sufficient conditions on both these dispatching and updating strategies to achieve good performance in terms of throughput and delay optimality. It turns out that this recent result also resolves a recent question that somebody had put in one of their paper, David Lipschutz, which asked the question, can you prove heavy traffic delay optimality when using delayed information, not using the actual information? Turns out you can. All right, so here is an illustration of this LED framework. So let's take, in this case, 3 servers. So you have 1, 2, 3, and let's say you have 2 dispatchers. And let's look at a policy like local join shortest queue. So it's basically joining the shortest queue, but just from its own local view without sampling all of the queues. So dispatcher 1 thinks that server 1 has 5 tasks, server 2 has 0 tasks, and server 3 has 1 task. Dispatcher 2 thinks server 1 has 4 tasks, server 2 has 2 tasks, and server 1 has 1 task. So what dispatcher 1 will do is basically, since it believes that server 2 has 0 tasks, it'll send an arriving task to server 2. And dispatcher 2 will send an arriving task to server 3 because it believes that that's the server that has the smallest task, right? So in this case, the memory, you know, in the dispatcher now keeps queue length information rather than just 0, 1. But this memory could be, as you can see, clearly false. It doesn't know the actual queue lengths of the server. And in fact, the estimation error actually helps avoid herd behavior, right? Because otherwise what will happen if these both of them knew that server 2 actually had the shortest queue, then both of them would send packets to server 2, causing potential congestion, right? So for example, if you had 5 such servers that all knew the exact states of these, 5 such dispatchers that all knew the exact states of these servers, then they would all send packets to server 2, and server 2's queue length would basically blow up. So that's called herd behavior. Anyway, very quickly to summarize this, I will just summarize one part of it, which is about heavy traffic delay optimality. So basically, it says that, our result says that if you can come up with any load balancing policy that's strictly better than random routing, okay, and it makes sure that at least once in a while, it provides you the true estimates of the queue length. It doesn't have to be in every time slot, but with certain probability P. Then the expected, from an expected delay point of view in heavy traffic, you will achieve heavy traffic delay optimality. That's all it says. So so these distributions that are strictly better than random routing are called delta tilted distributions. So for example, a delta tilted strategy could be local join shortest queue, that's better than random routing. Local join below some average, that's better than random routing. Or local, randomly pick these servers and choose to join one with as the smallest localist. That's again better than random. And the update strategy could be push-based or pull-based. So in the push-based strategy, what you would do is you'd randomly sample D servers and update their local estimate with a certain probability. In the pull-based, each server, when there are completed jobs, randomly samples a dispatcher and then says, hey, if I'm idle, I have to report this with probability 1. Otherwise, I only report it with a certain probability P tilde. And as long as P tilde is greater than 0, everything works out. So as you can see, there's a low message overhead, very low dispatching delay, low computational complexity, and appealing performance, it turns out, across a range of utilizations. And so, here we compare these policies, these LED policies, with traditional policies like the actual join shortest queue for multiple dispatcher, which sort of displays herd behavior and does poorly. And you can see that the local policies actually, which are sort of all year, do much better. So since I'm running out of time, I'll sort of skip some of these and jump to the conclusion, which is that we've developed a simple dynamic threshold-based policy, JBT-R, that achieves heavy traffic delay optimality in load balancing systems, and kind of show that this threshold R must grow with the traffic load, but not too fast. We've also developed a general framework, okay, for multi-dispatcher case in which a large class of policies, you can design clever ones that are heavy traffic delay optimal as well as throughput optimal. But there are several ongoing and open research questions which are interesting to study. A very technical question is whether the logarithmic growth rate in terms of the threshold is necessary for heavy traffic optimality. I believe it's most likely true. We actually do need logarithmic growth, but it's a very hard problem to actually show. From a practical point of view, this is not a very impactful problem. So we sort of decided not to study it because we already know that as long as you have, a logarithmic growth, you can achieve heavy traffic optimality. Among the class of these various heavy traffic optimal thresholds, there are quite a few you can show. Is there an optimal one? This is a very interesting question. We are looking at it. It requires an investigation into non-asymptotic regimes, which is quite interesting, and look, goes further into details beyond just heavy traffic delay optimality, but delay optimality more general. Then one question is, okay, we've shown heavy traffic optimality distribution. I mean, in the mean, in terms of the mean delay, can you show it in terms of the delay distribution itself? Turns out that you can, if you are basically looking for the sum of the Q lengths, you can use some moment generating function method to do it. But if you're looking at a multi-dimensional state space collapse for higher moments, this becomes a harder problem. We've also sort of started to look at problems involving convergence rates, where we've used some techniques, from Stein's approaches in order to characterize the convergence rates. A big question is that it seems like these load balancing policies can be analyzed, with this new class of tools and techniques in the heavy traffic domain. Can we somehow use this intuition for looking at other problems like scheduling problems, which generally have interference and things like that in it, which become harder to analyze, multicasting, caching? That's a very, very open question. And what we've done is, for a limited class of problems, we've shown some sample path of equivalence between scheduling and multicasting policies and some of these load balancing policies. So the answer has been sort of yes. And the big question is, can you go beyond heavy traffic optimality? You can easily come up with bizarre policies that are heavy traffic optimal, but may not be good in practice. And so we need other tools to differentiate good policies from bad ones. And we've looked into that problem a little bit too. We've sort of created another metric of performance called degree of Q imbalance, which helps overcome some of the limitations of these, of just looking at heavy traffic delay optimality. And this is where I'll stop. Thank you. Question?
Right. Yeah. Thanks for the great talk. So any questions from the audience? Yeah, first of all, let me give Professor Shroff a round of applause. But due to this kind of virtual format, we cannot really applause. So yeah, so sorry for that. So again, please ask questions if you have anything.
So I couldn't hear the question at all.
Yeah.
Do you want to put it in chat, perhaps?
Yeah. Gianfranco, your voice is breaking up, so I don't know why. Maybe you can put it in the chat, and then Professor Shroff can look at it.
Anyone else while the question is coming in chat?
Yeah, I just have a simple question. So the traffic probably varies by day or by hour or by minute.
Sure.
Is it possible to have some dynamic estimator running at the dispatcher's end, so to change its behavior based on the volume of the traffic that's coming in for the packet?
Yeah, and so that way you can change the load based on the traffic.
Yeah.
So, yeah, certainly you can do that.
Has anything been done on that or not? Is it reliable?
Yeah, so we actually proposed a different approach. So while we were able to prove this result, in terms of the actual implementation, we actually did simply this. So we randomly sample, DQs and take the minimum of the Q length as a threshold. So this policy satisfies the sufficient condition. So this policy is completely dynamic. So you don't need to measure the traffic.
Mm-hmm.
Okay. How to do that directly. Yeah. So it's
random sampling.
work around. Yeah.
Okay.
I think I see the question, and I mean, I see that there is something in chat. Okay, oops. Oh. Somehow, maybe I have to stop my sharing.
Yeah, I can read the question for you. So the question is, are the service time exponential
No,
of
no,
some
no.
lambda IID for all servers?
They're not. They're not exponential, right? So in fact, that was the original conjecture that needed them to be exponential, but we don't. Right? So we can allow any general distribution as long as it's light-tailed. And they don't need to be IID across the servers. So as long as they're independent across servers, they're fine. So the service time of a task just needs to be independent across servers. So one server could be fast, another server could be slow.
Okay. Any more questions? Okay, so if there's no more question, and the time is also getting late, so if no more question, then we can stop here. And again, thanks so much for coming to give this very, very nice talk. Let's thank Professor Shroff again. So so we can adjourn, I think. Yeah.
All right, thanks everyone. Really
Thanks, Les, for coming to deliver the talk. Great.
My pleasure.
Very
Thank you.
interesting.
Thank you.
Thank you.